In this video, I'd like to start chapter 2, which is 2D kinematics, which is looking at motion in more than one direction. So not just motion like this, but motion that can also be in this direction at the same time. But to start with, we're actually going to keep things to one dimension. We're just going to look at what happens if that dimension is vertical. So motion in the vertical direction in some ways can be the same as motion in the horizontal direction. What makes things different about a lot of vertical motion is much of the problems and systems we're looking at, things moving with a vertical velocity on the surface of Earth, meaning like away, moving away from or towards the ground. There's something special about that, and let me demonstrate. I guess I'll demonstrate with the eraser. So I let go of the eraser and it fell, surprising none of you. But there's something about that motion that that we can't, why did it move? I guess I didn't throw it down, right? I just let go. And the answer is it's because of gravity. So gravity causes objects to undergo an acceleration when nothing else is touching them. If things are touching them, gravity is still exerting an influence, but we'll learn about what's going on there in chapter 3 and 4. The point is, an object that's not touching anything else, but is still near the surface of the Earth, is going to accelerate towards the Earth at a very special rate. So in general, objects accelerate downward, and they do so all at the same rate. So our acceleration in the y direction, so this is now a in the y direction, before we've been talking about motion in the x direction, so we have our x acceleration. Our y acceleration is minus 9.8 meters per second squared. And this is true for all objects. I should admit this can change a little bit if something is moving fast enough for the air to really affect its motion, but for most things and for everything in this class, we're going to ignore that and pretend like this is always true. This number is used very, very often, and we're going to continue using it through, I think, every chapter the rest of the semester. So this 9.8 meters per second, we give it its own name because it's used so commonly. So we call that g, lowercase g, and g is defined as positive 9.8 meters per second squared, which means our y acceleration is equal to minus g. Okay, so let's do a little example using this. So let's say your instructor has an eraser and drops it from, a height of 1 meter. And it falls and hits the ground. So let's draw a picture. I guess I'll draw the pair going all the way down here. Okay, so it starts up here, it ends down here. I let go of it without throwing it downward, right? So that means that its initial velocity at the top was 0. Letting go of something is kind of a hint that initial velocity is 0. Because this acceleration is negative, we know that v final is equal to v initial plus at. So this is equal to v initial minus 9.8 times t, and v initial is 0, so this is just minus 9.8 times t. So as time goes by, it looks like our velocity becomes more and more negative. After 1 second, we would have a negative velocity of 9.8 meters per second, so that's going pretty fast towards the ground. So I said that this block fell a distance of 1 meter, and we're not, I'm not being careful, this isn't a real problem or whatever, so I should define, at least for you guys, that my y-axis is like this. So this is the plus y direction up, and that's why my negative velocity is down. If this falls a distance of 1 meter, that means my change in y, my vertical displacement, is equal to minus 1 meter. So that's what we're kind of being given in this problem. And so what that lets us do now is we can figure out, let's just figure out how long it takes this block to hit the ground. So we want t, and we know this displacement, we know the acceleration, we know the initial velocity. It turns out our position equation, x final equals x initial plus v initial t plus 1/2 at squared equation works. Now we're talking about motion in the y direction, of course. So all we have to do is change our x's to y's and make sure that this initial velocity is our initial velocity in the y direction. Sometimes I put the x or y subscript here. Sometimes I don't when it's clear we're only dealing with one direction. But here I'll put it explicitly. Okay, so our initial velocity is 0, so that goes away. We know our acceleration is minus 9.8, and we know if we move the y initial to the other side, y final minus y initial, that is our displacement, right? So this is minus 1 meters. So I have minus 1, I already moved that over, so I have minus 1 equals, this is 0, so I have 1/2 times a minus 9.8 times t squared. So now we just have to solve for t. Our minus signs cancel, and we have 2 divided by 9.8. So multiply both sides by 2, divide both sides by 9.8, and the t is squared, so I need to take the square root. So the square root of 2 over 9.8 is approximately 0.45, 0.452, but we'll round it to that. So an object dropped from a height of 1 meter on Earth will take 0.45 seconds to hit the ground, to fall that 1 meter. We can have different values of g, and this well, for the geologists in the class, this does happen a little bit at different points over the surface of the Earth. You can kind of make a map of the density of Earth's crust by measuring how this g value changes from place to place, and we're talking about changes of 1 part in 1,000 or 1 part in 10,000 or something. So we're only worried about 2 sig figs for our g for this class, so everything's 9.8. That's fine. But it varies a little bit across the surface of the Earth, a tiny bit. If you go further away from Earth, like higher up in the atmosphere and into space, this value gets smaller as you move further away from Earth, where its gravity gets weaker. More about that in chapter 4. And on the surface of other planets, because they have different gravitational attractions, you can have different values of g on the surface. So for instance, on the moon, g is approximately 1.6. I think it's about 1/6 the acceleration of gravity on Earth. And yeah, so that's why, things fall more slowly, and as a consequence, you can jump higher on the surface of the moon.